to the Journey Chez Chem. Today's warm-up are review from what we learned yesterday. So do the best you can, and I'll see you in a moment. Number one, the first thing that we do is write a table of our variables. And we are given volume and temperature. And we are going to standard temperature. And then I realized that with volume and temperature, it must be Charles's law. V1 divided by T1 equals V2 divided by T2. And therefore, V2 equals V1 divided by T1. And to undo division, I must multiply T2. And once I get this rearranged, then I just substitute in my values. And I have 500 milliliters, and T2 is 273 Kelvin, divided by 353 Kelvin. And when I do the math, I get 386.6855, and my Kelvin cancel, and that leaves me milliliters. Then I look back to my original problem and see the number with the least number of significant digits is how I express my answer. And that would be 1. 1 in 500, there's 1. Not in the chart, but in the original problem, we were given 500 milliliters. And therefore, my answer is the 8 rounds of 3 up, 400 milliliters. And that's the answer to number 1. Again, for number 2, the first thing that I do is write a table of my variables. And I'm given volume and pressure too is my unknown. And when I have volume and pressure, that's Boyle's law. And Boyle's law is V1 P1 equals V2 P2. I'm solving for P2. Therefore, P2 equals V1 P1 over V2. Now, I need to be able to rearrange any of these equations algebraically in order to determine my unknown. Once I get my rearranged equation, I just put in the values. And I have 55.3 centimeters cubed. P1 is 121 kPa, and divided by V2, which is 24.1 centimeters cubed. And then mathematically, when I solve this problem, I get 277.6473. I look back to my original problem, and the number with the least number of significant digits would be 3. And therefore, the 6 will round the 7 up. And my final answer will be 278 centimeters cubed. Oh, it's not centimeters cubed. Look at this. Centimeters cubed cancel. It has to be kPa for pressure. It's always important to follow through with the units. And notice that I am canceling my correct units. We all have to follow those rules. So that's the answer to number 2, 278 kilopascal. On worksheet B, first we are going to discuss the combined gas law, and we will be doing the sample problems together. Well, the combined gas law is Boyle's law, V2P2, and Charles's law that we have put together, and that's why we call it the combined gas law. And we do this very similarly to what we've done before. We make a chart of our variables. And V1 is 852 milliliters. And my P1 is 320 torr. And my initial temperature is 12 degrees Celsius plus 273. We always must have Kelvin and gas laws. And that would be 285 Kelvin. My V2 is my unknown. My P2 is 850 torr. And my T2 is 125 degrees Celsius. And when I add 273, I get 398 Kelvin. And as long as my pressures are in the same unit, that's fine. I don't need to do any conversion. But remember that your units must be consistent. Now I'm solving for V2. Therefore, V2 is equal to V1P1 times T2. To undo division, I must multiply. Then to undo multiplication, I must divide. And therefore, it is divided by T1 P2. Then I substitute in the values from my chart, and that would be 852 milliliters and 320 torr times 398 Kelvin divided by 285 Kelvin and 850 torr. Notice that my torr cancel and my Kelvin cancel. And when I do this mathematically, I come out with 447.9286. I look back to my original problem and I need 3 significant digits. And I look at the 9 and it rounds the 7 up. And therefore my final answer is 448 milliliters. And that's how you do the combined gas law. Now these problems are some of my most favorite because I get to have a cow. Well, what does that mean, having a cow? Well, it's a little shortened abbreviation to have a little bit of fun for collected over water. When we collected over water, we call it having a cow. And it's very, very important process in gas laws because it makes it very easy for us to obtain gases by collecting them over water. And we will be doing a lab in a few weeks on this. Now what this looks like is here is a beaker with water. And the way I'm going to do this for us in the lab is that we're going to take a small amount of magnesium ribbon and we're going to throw it into the water. And we're throw it in there because we must break the surface tension. And then we are going to take a gas collecting tube that looks like this. And it has graduations in milliliters here. And we will put hydrochloric acid in it, and the remainder will be water, and we'll practice this first with water. And then we will quickly tip it upside down and put it in the water right over that magnesium. And then the hydrochloric acid will come down and meet with the magnesium, and the reaction will occur. This reaction is that we have the magnesium plus the hydrochloric acid. And we've had this before. We know that the magnesium is going to displace the positive hydrogen, and we will get magnesium chloride and hydrogen gas. Now we had done this once before where we found the empirical formula for the magnesium chloride last semester. But now we're interested in this hydrogen. And I will quickly invert this upside down over top, and therefore I have my gas collecting tube, and I know that students always love my diagrams. And so I flip it upside down, and maybe this is a bit rounder, and I will have my initial volume of the material in this tube, and it's graduated so we have milliliters. And then when the magnesium and the hydrochloric acid meet, the reaction happens, and you're just going to love how that reaction goes. And then we'll come out with a final volume, because it's going to bubble and it's going to displace, and the gas will be collected over this water. And this here will be the hydrogen collected. Now, because we collect it over the water, our pressure that we have includes the pressure of the water. And Dalton's law tells us that the pressure of the total is equal to the pressure of the dry gas plus the pressure of the water. And the way that we're going to use this is we want to figure out the pressure of the dry gas. And therefore, the pressure of the dry gas is equal to the pressure of the total, which would be of the barometric pressure that it's collected at, minus the pressure of water. And we have a chart that gives us the pressure of water at different temperatures. Now, it's interesting. What would the pressure of the water be at sea level when it's boiling? Well, we know that boiling occurs when the surrounding pressure is equal to the vapor pressure of the liquid, and at sea level, that would be 101.3 kPa. However, at different temperatures, water will have different pressures. And we will have a chart, and on the assessments and on the quizzes, I will give you those values, so you don't have to worry about those. But you do have a chart to help you with the problems that you may need to pull out when you're doing your assignment tonight. And that's how we use Dalton's law. In these problems now, we're going to be using Dalton's law and the combined gas law. Dalton's law to figure out our pressure of the dry gas. And I'll go over that with you in a moment. Now, on worksheet B, the side that has Dalton's law and the combined gas law, we're doing the example problem. And first thing I always do is make a chart of my variables. Now, I was given 450 centimeters cubed. Now, because this is collected over water, or it's having a cow, we know that we must use Dalton's law in order to get my P1, or the pressure of the dry gas. Now, in this problem, we were given that the pressure was 45 kPa. Now, that is the total pressure, and I must subtract the pressure of the water at 20 degrees Celsius. And when I look on the chart, I see that that value is 2.3 kPa. And therefore, the pressure of the dry gas is 42.7 kPa. That is very important. That is the pressure of the dry gas in order to get my P1. Because I don't want the water vapor pressure in there as well when we collect it over water. And then I fill in the rest of the values as given in the problem, and we've done this with the combined gas law. Now, then I have the combined gas law. V1 P1 over T1 equals V2 P2 over T2. Therefore, V2 equals V1 P1 T2 divided by T1 P2. And when I have a nice chart this way, I just fill in the numbers. And therefore, my V1 is 450 centimeters cubed. My P1 is 42.7 kPa. And that was the one different part of this where we're using Dalton's law. And my T2 is standard temperature. And I divide it by my T1, which is 450 centimeters cubed. Oh, that can't be right. T1 is the temperature. It's 293 Kelvin. And my P2 is 95 kPa. And you can see how very important it is to follow my table and to follow my equation, because mistakes can easily be made. Now, when I do the math here, I'm going to get 188.4567. Then I look back to my original problem, and the number with the least number of significant digits is 2. And therefore, I look at this 8, and it rounds the 8 up, and my final answer is 190 centimeters cubed. Because my Kelvin cancels and my kPa cancels, giving me centimeters cubed. And that's how you do those two types of problems. We have a combined gas law and Dalton's law. And the worksheet that you have tonight, one side is combined gas law and the other side is both. And I know you can do it, and I just can't wait to see you tomorrow. Remember, we're going to have all these problems all mixed up for a quiz, and then we'll have the assessment. And you can look on your guide to see when that's upcoming. Well, that was some fun, and thank you for being here, and I can't wait to see you tomorrow.